Okay, let's continue our analysis of what's going on in this integral. Recall that we're trying to find the integral from negative infinity to infinity of the function f of x, and we've made the assumption that f of x is a rational function and the degree of the denominator is at least 2 bigger than the degree of the numerator. We replaced all of the x's with z's, so we now have a function f of z equals p of z over q of z, where the degree of the denominator is at least 2 bigger than the degree of the numerator. And we use the residue theorem to show that the integral around this closed curve is equal to 2 pi I times the sum of the residues for all of the poles that are in the upper half plane. Now, since this closed curve is made up of a horizontal line segment together with a semicircle, we could split up the integral around C to be the sum of the integral along the line segment plus the integral along the semicircle. Let's now parameterize and look at each one of these integrals separately. Let's do the easy one first. The easy one is the line segment. Since this is a piece of the x-axis, we know that y is equal to 0. And we could set x equal to t, but I'm simply going to let x equal x. So that's my parameterization of the line segment. Now, since in the Argand plane, z is equal to x plus I times y, if I substitute in, I get z equals x plus 0i, so just z equals x. So dz is equal to dx. And notice that if I want to go from negative r to r along the horizontal axis, that's going to correspond to letting x go from negative r to r. So let's substitute that into our integral. We have the integral along L sub r of f of z dz. That becomes the integral from negative r to r. I'm replacing z with x, and dz is the same as dx. And now let's take the limit as r goes to infinity. Well, if I let r go to infinity, then this becomes the integral from negative infinity to infinity, f of x dx, which is exactly what I'm looking for. So if I take the limit as x goes to infinity, this integral over here gives us the integral we're looking for. So that one is a keeper. Now let's look at what's happening with the integral over the semicircle. The way that we can parameterize a circle of radius r is we can let x equal r cosine theta and y equal r sine theta. So writing this in terms of z's, z equals r cosine theta. Well, let me just remind you, z is x plus I times y. So that will be r cosine theta plus I times r sine theta. If we factor out the r, then that's cosine theta plus I sine theta. And you might recognize this from Euler's theorem or Euler's formula. This is the same as r e to the I theta. And it's going to be easier to think about it that way. So we can parameterize the semicircle by letting z equal r e to the I theta. And since I only want the upper half, I'm going to let theta go from 0 to pi. Now when I do the integral, I also have to substitute in the differential dz. dz is going to be r times the derivative of e to the I theta is I e to the I theta, and then d theta. So this is going to be what we substitute in here. Now remember, f of z is equal to the quotient of two polynomials, p of z over q of z. So just writing down the first term or so of each, P is going to be of the form a sub m z to the m plus some lower order terms. And Q is going to be of the form b sub n z to the n plus some lower order terms. And remember, we're assuming that n is at least 2 more than m. So if I substitute in r e to the I theta for z, and then multiply by dz, which is r I e to the I theta d theta. Let's see what we get. This will be the integral from 0 to pi of a sub m, and then I have to take z to the mth power. So that'll be r to the m e to the I m theta plus some lower order terms. And on the bottom, I'll have b sub n r to the n e to the I n theta plus lower order terms. And then that's multiplied by r I e to the I theta d theta. Let's pay particular attention to the powers of r. Let me factor out the highest power of r from the top and the bottom. So we've got the integral along SR of f of z dz equals. In the numerator, I have an r to the m plus some lower powers of r, multiplied by this r that came from the differential. So I have an r to the m plus 1 on top. And the biggest power of r in the denominator is r to the n. Now, since I'm integrating with respect to theta, we're treating those r's as constants, and I can actually factor those completely out of the integral. So if I do that, I have r to the n plus 1 over r to the n times a sub m e to the I m theta plus some lower order terms over b sub n e to the I n theta plus some lower order terms times I e to the I theta d theta. Now, some of these lower order terms are still going to have r's in them for sure, but we factored out the dominant terms, the biggest powers of r. Now, this is the step which is going to be a leap of faith for you, although I did have you work out one specific example in one of your graded homework problems. This integral with respect to theta is going to be bounded. And then we're going to multiply that by r to the m plus 1 over r to the n. Now remember, we've made the assumption that the degree of the denominator is at least 2 bigger than the degree of the numerator. So that means that r to the n is bigger than r to the n plus 1. So as r goes to infinity, this coefficient is going to 0. So if I take something which is bounded and I multiply it by something which is going to 0, then I get something which is going to 0 as r goes to infinity. Now, to prove that this actually goes to 0 involves a fair amount of analysis. You got a taste of that in an earlier homework assignment. But that's going to be something I'm just going to let you assume, provided we have a rational function where the degree of the denominator is at least 2 bigger than the degree of the numerator. Hopefully you can at least see why we want it to be at least 1 bigger, because after I take the r from the differential and multiply it into the numerator, that already increases the power of the numerator by 1. So if I want this part to be bottom heavy, in order for the degree of the bottom to be bigger, then the degree of the denominator needs to be at least 1 more it has to be more than 1 bigger than the degree of the numerator. So let's recap. Let's see what we've got. From the discussion in the previous video, we know that the sum of these two integrals is equal to the sum of the residues times 2 pi I. And then, if we let r go to infinity, this first integral becomes the integral from negative infinity to infinity of f of x dx. And the second one becomes 0. So the big conclusion is that the integral from negative infinity to infinity of f of x dx is equal to the sum of over all the poles in the upper half plane of the residues of f of z at those poles. And the assumptions for this to be true were that the function f had to be 3 things. It had to be a rational function, the degree of the denominator had to be at least 2 bigger than the degree of the numerator, and f could not have any real zeros in the denominator. In other words, q can't have any zeros along the real axis.